Hello, my name is Rebecca Muller. During today's lesson, we're going to look at how to solve some exponential and logarithmic expressions and equations and inequalities. We've already seen how to solve exponential equations where we could easily get the same base. But what we want to consider is, what if we're not able to do that? Let's look at some properties of exponential and logarithmic equations which are going to help us. If we have a base greater than 0 and not equal to 1, then if b to the x equals b to the y, then x equals y, and vice versa. If we know x equals y, then b to the x is going to equal b to the y. That's how we interpret that if and only if statement. Also, if x and y are both positive numbers, then log base b of x is equal to log base b of y if and only if x equals y. Now, we're going to look at our first example, and that's going to have to do with a case where we have an exponential function where the bases are not easily converted to each other, to be the same base. We want to look at solving the equation 2 to the x plus 3 equals 5 to the x analytically. Once we've completed that solution, then we're going to look at the inequalities that we can find, that we have associated with that equation. That is, we'll look at solving 2 to the x plus 3 is greater than or equal to 5 to the x, and we'll do that by using the answers to the equation and the graph. And we'll also solve the inequality where 2 to the x plus 3 is less than or equal to 5 to the x in the same manner. Let's begin by looking at the equation 2 to the x plus 3 equals 5 to the x. Now, you may recall that one of the properties that we had at the beginning of the section told us that if we have x equal to y, then we can write log base b of x equals log base b of y. We're going to use that property in this example. When you're given a choice, because of the fact that your calculator will do both common logarithms and natural logarithms, that's probably the base that you would like to use. In this case, we're going to use the common logarithm. And our first step will be to take the logarithm of both sides of the equation. This is what it looks like. We're going to write down the log of 2 to the x plus 3 equals the log of 5 to the x power. Now, the reason this process helps us has to do with the fact that we have properties of logarithms that we can apply at this point. Namely, the property that we want to use is the one that tells us that we can take a logarithm where the anti-logarithm is written to a power and take that power and pull it into front as a factor. What that looks like is this: x plus 3 multiplied times the log of 2 will now equal x multiplied times the log of 5. This, in effect, changes this equation so we don't have exponents anymore. We'll now use distributive property on the left-hand side. X times the log of 2 plus 3 times the log of 2 is going to equal x times the log of 5. Now, when you're working with logarithms, recall that the logarithm of 2 is simply a constant value. There's no variable here. So it's just like having a coefficient on x. We have two terms in this equation which involve x. Just like we would do in a simple linear equation, what we'll do is try to get the x's on the same side of the equation and put the constant values on the other side. Namely, what I want to do is take the first term and the second term and make sure we have them on the same side of the equation. And we'll take the constant term, the one without the variable, and we'll put it on the opposite side of the equation. Here's what that's going to look like. We'll subtract x log 5 from both sides of the equation and write down x log 2 minus x times log 5 on the left-hand side. In the same step, what I'm going to do is take the constant and subtract it from both sides of the equation to give us negative 3 log 2. Now, I want to pick up with this equation and give myself a little bit more room. And what we want to now look at is the fact that if we're trying to solve for x, we notice that in the two terms on the left, we have x as a common factor. Let's factor x out of those two terms. We'll have x multiplied times the log of 2 minus the log of 5 in parentheses equals negative 3 times the log of 2. The operation that is going on between x and the expression in parentheses is multiplication. And so in order to undo the multiplication, we can use division. We're going to divide then both sides of this equation by the expression in parentheses. That will give us x equals negative 3 times the log of 2 divided by the log of 2 minus the log of 5. Now at this point, if you were using a calculator, you could go ahead and substitute these values in. Another thing that we might want to do is to use the properties of logarithms in order to simplify, in some respects, some of the expressions that we have here. Namely, what I'm going to do is use the fact that in the numerator, I can write this expression, instead of negative 3 times the log of 2, I'll take the negative 3, place it in the exponent power, and have log of 2 to the negative 3, or log of 1/8. 2 to the negative 3, recall, is equal to that. In the denominator, I have a difference of two logarithms. I can use the property of logarithms, which states that I can rewrite this as a log of a quotient. So instead of log of 2 minus log of 5, it can be written as the log of 2/5. Now what I want to look at are the inequalities that were associated with this problem. You may recall that on the original screen, we had 2 to the x plus 3 greater than or equal to 5x, and 2 to the x plus 3 less than or equal to 5x that we were going to try to solve. What we want to look at is the graph of these two functions. Well, we're going to set them up as two functions. We're going to take the left-hand side of the equation and put it into y sub 1, and the right-hand side of the equation and put it into y sub 2, and then look at where one is above the other on the graph. Let's do that now. In our y equals key, we want to put into y sub 1 2 raised to the x plus 3 power. Then, in our y sub 2 key, we're going to place 5 raised to the x power. Now, I'm going to change my window so that I get a better picture of this problem. I've already done the problem previously, so I know that I want to look at something that's a little bit larger than our standard screen. I'm changing the window so that my y values are a little bit further apart and my x values a little closer. Here we're getting the graph of y sub 1, which is, remember, 2 to the x plus 3 first. Then we see the graph of y equals 5 to the x. The point of intersection is going to be equivalent to the solution of the equation which we just found, which, recall, in exact form was log of 1/8 divided by log of 2/5. Notice that we can use our trace key to tell which graph that we're looking at. At this point, in the upper left-hand corner, notice we're looking at y sub 1. Here, y sub 1 is greater than y sub 2. It's above that graph. So we can see that from negative infinity until we get to the intersection point, what we have is the graph, the 2 to the x plus 3 greater than 5 to the x. Once we move past that point of intersection, though, the graph of y sub 1 is below the graph of y sub 2, and therefore we have the solution to the other part of the inequality. Let's now look at what those solutions are going to end up looking like. We can say then that the 2 to the x plus 3 was greater than or equal to 5 to the x when we had negative infinity up until that point, log of 1/8 divided by log of 2/5. We have 2 to the x plus 3 less than or equal to 5 to the x when we have, from that point of intersection, I need brackets here because of the inclusion. Let's make sure we have that correct. We need to put brackets to include that endpoint, log of 1/8 divided by log of 2/5 to infinity. Now, let's see if you can try a problem on your own, and here is your example. We want to solve the exponential equation, solve 3 to the x plus 2 equals 5 analytically. Then find both an exact and an approximate answer. Once you've done that, let's solve that inequality, 3 to the x plus 2 is greater than 5, by using your answer to part 1 and the graph, and then solve 3 to the x plus 2 is less than 5 in the same manner. We want to give both exact and approximate answers. Turn off the tape now and try the problem, and then turn the tape back on in order to see the correct solution. Let's see how you did. We're going to begin with the equation. 3 to the x plus 2 equals 5. In a manner similar to our first example, we're going to begin by taking the logarithm of both sides of the equation. So we'll write log of 3 to the x plus 2 equals log of 5. Next, using this property that we had previously, we're going to take the exponent and write it as a factor in front of log 3. Distributive property should have come next. X times log 3 plus 2 times log 3 equals the log of 5. At this point in the problem, note that you have only a single term which involves the variable x. For that reason, we can isolate this term by subtracting off the other part of that side of the equation, 2 log 3. That will look like this. X times the log of 3 equals the log of 5 minus 2 log 3. Finally, because x is being multiplied times the log of 3 in this step, we can go ahead and divide in order to get a value of x. We'll get x equals log of 5 minus 2 times log 3 divided by log 3. In a manner similar to what we did in the last problem, we're going to use the properties of logarithms to rewrite this. X equals, in the numerator, I'll use two properties at once. First, notice that the 2 can be written as an exponent, and I'll have the log of 9. And second, notice that we have a difference of logs, and putting those together, I can write this as the log of 5/9. In the denominator, we had a single term, log of 3. Next, let's look at the calculator in order to try to find out where these two equations intersect, and then see if that verifies what we found analytically. And also in the same frame, what we're going to consider is when is one side of the equation greater than the other side, and that is when are the two sides of the equation going to be one above the other. Let's do that now. We'll go back to our y equals key, and I'm putting in for y1 3 raised to the x plus 2 power. For y sub 2, we'll look at 5. I'm going to go into my standard screen to see what kinds of solutions we end up with here. Notice that the second equation gave us a horizontal line. Let's find the point of intersection of these two equations first. We're going to calculate the intersection point. Here's y1, y2, and intersection. Now, what we have here is an intersection point where the x value is negative 0.535 approximately. What we're going to do is check out the solution we had on our equation that we had in exact form. That is, we had in the numerator the log of 5/9, and we were dividing that by the log of 3. Notice that we get the same value for x that we had found when we did it graphically. So that verifies the solution to our equation. The next thing we want to consider is where are the two graphs, where is one of the graphs below the other? The graph which is exponential was the left-hand side of the equation, 3 to the x plus 2 power. The horizontal line was the right-hand side of the equation, which was 5. The point of intersection, as we found previously, is approximately negative 0.535. Notice that the exponential part is below the horizontal part from negative infinity until that point of intersection, and above it past that. Let's look at how we'll write the solution sets in interval notation to these inequalities. In our first part, we have written down the solution to 3 to the x plus 2 is greater than 5. On the left, we have written it in its exact form. and that is to take the point of intersection as it is exactly and go towards infinity. On the right-hand side, we have the solution as it would be written in its approximate form, from negative 0.3535 to infinity. At the bottom of the screen, you'll note that we have the solution to the inequality 3dx plus 2 is less than 5 in the same manner. First the exact answer, and then the approximate answer. Now let's look at another example where we're going to be dealing with a logarithmic equation, an equation that begins with logarithms instead of us inserting those into the equation. Our example is log base 5 of x plus 2 plus log base 5 of x minus 2 equals 1. Now we're going to use the properties of logarithms again in order to simplify this equation. Namely, we have the sum of two logarithms. Let's rewrite that as the logarithm, base 5, of the product of these two antilogs, that is x plus 2 times x minus 2. We can multiply that out and get x squared minus 4. Next, as a logarithmic equation, this is all we can do with the properties that we have at hand. But what we also have learned is that we can change a logarithmic equation into its exponential format, and that's how we'll approach the problem now. We're going to remember that a logarithmic equation has an equivalent exponential form, and in this case we have base 5 raised to the first power equals x squared minus 4. Let's add 4 to both sides of the equation. 9 equals x squared. And solving for x gives us plus or minus 3 as a solution to the quadratic. Now, one thing about logarithms is that we recall that we have a restriction on the domains of logarithms. When we get two solutions here, both positive 3 and negative 3, we have to consider whether or not either of these answers is actually what is considered an extraneous root. Does it actually solve the original equation? Taking the value of 3, we can note that when x is equal to 3, we have log base 5 of 3 plus 2 is 5, plus, substituting in the second term, log base 5 of 3 minus 2, which is 1, and we want to see whether that equals 1. Log base 5 of 5 is 1, log of 1 for any base is 0, and this solution checks. However, when we try to substitute in the negative 3, note that right away we have log base 5 of negative 3 plus 2, which is negative 1, and that is an undefined term. We don't need to go any further because of the fact that negative numbers are not part of the domain of logarithms. In our next example, we want to look at an equation solving routine on our calculators. We're going to be using the TI-83 in order to solve the following equation. We want to find a solution to the following equation and then round that result to the nearest thousandth. And the equation is 1.5 raised to the log of x power equals e to the 0.5 power. Let's insert that into the calculator now. We're going to go to our math menu, and I'm going to press the up arrow to go to solver. You could also have scrolled down. Now at this point I didn't have an equation in my solver to begin with. If you had worked with the equation solver previously, you may have to press the up arrow to get to the right place here. Let's insert 1.5 raised to the expression log of x. Then we're going to have to subtract off the value of e to the 5th power, to the 0.5 power, that is. Now, the reason we had to do the subtraction is notice that the equation solver at the outset has the equation set equal to 0. We're now going to press enter, and it asks us to give a guess. At this point, you need to pick a positive number to plug in here because of the fact that you have to use the fact that logarithms have a domain of only positive entries. Here we have a value of 2. I can go ahead and use that. We're going to then use the solve key, which is under alpha enter on this calculator, and we notice that the answer is approximately 17.106. Here we're rounding off to the nearest thousandth. Now let's look at another example which combines methods that we've learned from quadratic equations, rational equations, and exponential equations. Here's the problem. We want to solve analytically the equation e to the x power minus 6 equals negative 8 raised to e to the x, divided by e to the x power. This is a rational equation to begin with because of the fractions, and we're going to, in our first step, multiply everything by that denominator, e to the x. Now, e to the x times e to the x is e to the 2x minus 6e to the x equals negative 8. Setting this equal to 0, e to the 2x minus 6e to the x plus 8 equals 0. And then notice that this is an equation of the quadratic type in that it has three terms. One of them is a square of the middle term's variable expression, and we're going to use factorization at this point in order to solve it. E to the 2x, recall, was e to the x times e to the x. The factors of 8 that add together to give us negative 6 are negative 4 and negative 2, and we have the factored format. Now set each of the factors equal to 0. The first part will tell us that e to the x could equal 4. The second part tells us e to the x could equal 2. In order to solve for x, what we can use is the fact that this is an exponential equation which can be changed to its logarithmic form. That is, the natural log of 4 equals x, and the natural log of 2 equals x. These are the two solutions to the original equation. In conclusion, what we'd like to do is review some of the things we've learned during this section. In solving exponential and logarithmic equations, we need to think about changing the equation into one of the following forms where a and b are real numbers, a is positive and not equal to 1, whenever we cannot solve it in its original format. The first form is a to the f of x equals b. We can solve an equation of this type by taking logarithms of each side. If we begin with a logarithmic equation, log base a of f of x equals log base a of g of x, then from the given equation, we can simply say f of x must equal g of x, and then solve analytically. If we have a logarithmic equation of the form log base a of f of x equals b, we can solve by using the definition of logarithm to write the expression in its exponential form as f of x equals a to the b power. There are several applications that you can look at in your textbook of these types of equations. Take some time now to solve a few.